Kent State University.
Thanks very much. I'm the only thing standing between you and so let me stretch things a little bit and tell you a story. And this work was funded initially by a little grant from the National Academies of Tech Futures Initiative, because no one in the right mind would let us start to look at these sorts of questions. And eventually, a computational neuroscience project. So I'll just go out on a limb and tell you that we're not going to predict anything. Not whether, not when the next asteroid will hit us, or seizures if you don't have an adequate model and you don't understand the processes. And you're going to need observer models, which you're going to have to fuse with data, which is the only way I know of that you do effective prediction for anything. So observer models that could be fused with data have been around for a while. Kalman actually came up with it, but Leuenberger's name has stuck. And in the old linear theory from the 1960s, the issue is if you have a system with some outputs, could you take a subset of the outputs, put it through a model of the system, and you generate what you can't observe? Linear systems are weird. Fortunately, they don't exist. But linear systems are strange because you don't need to actually understand the system to do this. You just need a model with enough degrees of freedom, and you end up reconstructing something that actually has some equivalence to what the underlying system does. Another interesting paper from 1970 is that every good regulator of a system, we would like to not just predict seizures for fun, you'd like to control them, has to be a model of that system. And of course, as we've been talking about, we have a lot of very good models now for the last 50 or 60 years for neurons, networks of neurons, neural fields. So we've become very sophisticated in that. And why can't you begin to use this with what we know about observing and controlling systems? So you can come up with a framework for what an engineer would do in order to make a model of the brain with whatever fun block diagrams you might want to use. There's an underlying system, you know something about it, you're going to have equations that describe this, or you could assume that the brain is some generalized linear model with a stochastic element to it, and use a black box statistical model. There's nothing wrong with that. We make a lot of progress with black box statistical models when we really don't know about the system to make a more fundamental one. And we always assume that there's some observer function. In general, we don't touch the underlying variables in any system. You can then make an observer model to that. And an observer model, they're called filters because they actually do filter out the dynamics you're interested in. This is how we build Google cars. This is how we do weather prediction. And if you're going to control things, we don't control weather, but we do control cars and airplanes, you want to take your measurements off the model so you understand what you're dealing with, and you pump it through your favorite control law into both the system and the model that you're using. So these are fairly well-established techniques. In the 1960s, Rudolph Kalman, really spurred on by the aerospace program in the United States, came up for linear systems, the functions are straight lines and planes. You could pump single solutions that might have bell-shaped uncertainty curves through them, and you get out single solutions with bell-shaped uncertainty curves. You can do this analytically, it's blazingly fast, and it works very well for things that linearize well. And for things that wiggle and are nonlinear, it becomes more complex. The way that engineers have generally applied this now is to take a cloud of points. This is where you get your 20% chance of, actually for Melbourne, it's an 80% chance of rain every day, with various percentages of other probabilities. You push it through your function that now might not be linearized, and it isn't for things like weather prediction, and you get up a series of potential solutions, and you might know something about your observation function, and then you make more measurements. The weather community does this in general. Short and medium-term forecasting is 6 hours. Whether it's, I know about the European and the North American programs, but I presume that Australia do exactly the same thing. And then you make new measurements and keep iterating these processes. So I'm not going to talk more about those filtering techniques. If you have an uncontrollable desire to learn everything about this, there is a book that tries to summarize some of this specifically for neuroscience. But let's talk a little bit about observability, because that's really the central issue, I think, in seizure prediction. And it's one that we haven't solved. What's happening in a system when you observe a piece of it, a network, for instance? In the 60s and 50s, we pretty much nailed this all down. And if you have a system that has some dynamics, and you have an observation function, forgive what I'll just show you. So some of you know this well, and some of you don't, but just bear with me for a moment. I'll show some pictures that explain things. Is there a solution to this set of equations to your model? And there are a number of ways of asking how to do that for differential equations, and you get something out. We've also learned in the last 2 decades that there's another way to do this, which is, can you build a function, a map, that represents what is going on in those systems? Turns out these are 2 different ways of asking if a system is observable. Rudolf Kalman in the early 60s wrote out what you would need to do in order to tell if a system is observable. What it is that you can reconstruct a number of independent variables in some way. And that was his test that he used with M matrix. So nonlinear observability, which is what we face in the nervous system, is not nearly as pleasant and simple as the last slide. I think that's why they don't teach it in medical school. By 1991, Jean-Jacques Slotin and Lee, in what is an enormously cited book on control theory, have written it all down. This is really all you need to do in order to apply this to neural systems, but it's complicated. And it takes derivatives of your observation function and applies them to the various pieces of your model. And these are called Lie derivatives, which is, again, really pictorially asking if you have a solution to an underlying system. Meaning there's something going on in a brain, and you might have, as Andre just talked about, some phase space where this set of dynamics flows. But you observe out here the measurements that you make, and the whole secret to this is when that underlying system flows, you see every twitch represented in what you measure. Which then leads to the next question. If the models represent brains, are the models or the brains observable? This isn't clear for any of the questions we have that we're interested in today, but I do think it brings up some interesting limits of knowledge problems. We like to fantasize that we can understand anything that we would like to measure, and we can model everything. At least I kind of hope that might be true, but it's not necessarily certain. So remember also, pictorially, for observability of nonlinear systems, you could also just make a map. There's a beautiful set of papers by Christophe Letellier, McGuire, and colleagues. Imagine you're measuring things from a brain network. You could, for instance, this is from a set of differential equations, but you can map it in different ways depending on what you observe. We have maps where there are folds, maps where your system is unfolded, maps where everything gets scrunched into a point at times. The observability of what you reconstruct is actually visually evident if you look at these maps. You can also make functions, which I'll show you in a minute, where you actually look at the quality of the mapping and you ask where it all scrunches together, because you're not observing anything there. When systems go through points or planes or even worse structures and flatten everything together, you lose your predictability, you lose your observability at those points. So you're looking for ways to unfold the dynamics you're interested in. And lastly, controllability, which is what we'd like to do with all of the various devices that Greg had mentioned to us. So I'll call this abstract driver's ed for a minute. You can't parallel park a sailboat. Sort of summarizes the issue. I'm a sailor who's trying to use one of those little sunfish, so I don't know a whole lot about sailing. But I do know that if the wind is blowing this way, you can't go straight into the wind, so you're limited to go and try to tack back and forth. And you need room to do that, because you can't go sideways in one of those things. You need room to park a car. There's a message to this. Control engineers have spent an awful lot of ink and paper trying to prove whether it is in fact possible to park a car. I do have a daughter who is an example of someone who cannot park a car, so not everyone can actually solve this problem in the algebra. But if you've got room, you turn the wheel and drive in or drive out. And if you don't have room, meaning the parking space is big enough for the car, but you can't turn the axis of the wheels, then you have a problem to go sideways, which is a degree of freedom that normally your car and your tires don't permit. So sailboats don't do this either, and the whole secret to nonlinear controllability ends up being, if I have a system that's running, it has dynamics. My car can go forward or backwards. And I then have a controller. Do I end up at the same place I start, which means you never get out of the parking spot, or can you come up with a scheme so you actually move a little bit? So the secret to parking, if you ever wondered what it is to zigzag. And if you just go left forward, right forward, and then go left backward and right backward, you don't quite end up where you start. You can prove you can get out of any parking space, especially if you happen to know how to work with Lie algebras on what they call vector fields. So there's a formula that looks a little like Kalman's formula, showing the control piece and the dynamics multiplied together in what asks if there's a little left over, a bracket, a little bit left over after you do one of the zigzag things. And seizures are instabilities on networks. So, can you observe simple networks? Which brings us back to Ching-Tai Lin in 1974. So this is one of the classics in control theory. Ching-Tai proved, and if you're interested, I can show you kind of how this works, but just visually, Ching-Tai proved that in linear networks, chains of nodes and these buds, which he called cactuses. I have no idea if this man ever saw a cactus. I don't think of cactuses. When I look at this, I think of lollipops. This is what a cactus looks like, but this is stuff. And you can go read papers in journals like Nature talking about cactuses now. But this is the topology of a network that's controllable. Have you folks seen this in brains, by the way? I mean, there's a problem here. So, Lynn used Kalman's criteria on simple networks with chains and bugs to say what would span a network in the brain, for instance, and enable you to control, or, as Resch and Perret showed a few years later, you can flip those arrows around and prove that you can observe such networks. So how about more complex networks than our little lollipop figures? This came out in Nature in 2011. This is Liu, Slotine, and Barabashi. They used Lynn structural controllability to ask if a wide variety of complex networks are indeed controllable. This is a critical paper for any conference on seizure prediction. They left out any symmetries in the networks because this is the old linear theory that doesn't allow that. They published then, 2 years later, in PNAS, the converse of this, which is the observability of complex networks, and again, assume that there are no symmetries. Symmetries give people fits when trying to ask if a network is observable or controllable. Romain Jolly, in a very complex paper, asked if a nonlinear network can be observed. And proves that it can, but only in the case where there are no symmetries. Barabashi and Slotine and Liu were so distressed by this that this is a quote from their PNAS paper. Any symmetries in the state variables that leave the inputs and the outputs and the derivatives and variables make the system unobservable, but it's okay because symmetries in state variables are very unlikely for large systems. Problem with this, which is the relationship between symmetry and synchrony. It was formalized by Marty Golubitsky and colleagues 3 years ago, which basically says that in a system with symmetries, you will see synchrony. And it's an if and only if statement. If you see synchrony in systems, you have to have underlying symmetries, which is when you look at a system like the brain, you see synchronization all the time. We know that it's both important in terms of things like binding information and in solving a number of important problems in the brain, like in sensory calculations, which we all know rather well. And then very recently, Lou Pecora and colleagues examined a range of complex networks, and it turns out that there's this marvelous, there are mathematicians with a lot of time on their hands, and they've worked out ways of looking at all of the symmetries in networks. So you feed it your favorite network, whether it was internet or power grids, which is really the hot field right now in this area, for brains, and you can generate all of the evidence symmetries in what people call the permutation group, which is you just take a network and you swap the components, you still end up with the same network. So here in random networks, if you go and take, I think this was 9 different vertices, and you can randomly pluck out a few connections, you can see thousands of symmetries in relatively small networks. And I highly recommend this paper, but it depended on group theory in order to do this. So what's a group? So I looked it up. A theory of groups is a branch of mathematics in which one does something to something and then compares the result with the result obtained from doing the same thing to something else, or something else to the same thing. That's James Newman's wonderful book in 1956. But really what it says is that you've got an element, set of elements of an operation, and when you do the operation like addition, you still end up with an integer. The law of association that we learned in grade school holds. There is an identity like 0 for addition, and there's an inverse, the minus. So not all groups are terribly complicated. Do any of you remember taking organic chemistry? They tortured us with that when I was in college. And one of the reasons that I think they did it was because group theory has revolutionized chemistry. The chemists realized long ago that if I gave you the formula, now these are molecules, but you can read them as brain networks. These are the neurons that you identify. You go and we'll set, for instance, we'll stick a whole bunch of neurons, and we can tell whether they're inhibitory, what kind of inhibitory neurons they are, what kind of excitatory cells. We do not, in general, know how they're hooked up. Well, if you were looking at molecules, these all have the same formula. They are not the same. They're not the same molecular structure or chemistry either. So these are called structural isomers. You can also have rotational isomers. This very nice book by Hargitay and Hargitay used some of Degas's paintings to illustrate some of these molecular symmetries. But basically, chemical reactions, all of crystallography depends on this. Buckyballs reveal the secret life of carbon in terms of these symmetries. The thalidomide problem was an issue of handedness of one of the types of thalidomide molecules. And of course, you have proteins with left-handed amino acids, but all of the nucleic acids are right-handed. So molecules are just networks. I think everything that you learn about in the groups in chemistry probably do apply to looking at neuronal systems. This paper by Song and colleagues looked at the highly overrepresented motifs in mammalian brain, and we're going to go and look at a bunch of these motifs right now. So here's 8 of my favorite motifs, and are they observable or controllable? So you can take the measures that I very briefly mentioned, and you can go and ask, how scrunched together are the metals? And some of it makes an awful lot of sense. Here's a network where everything is symmetric. So unless you break the symmetry, you actually expect that you can't observe or control these networks from any one node, and in fact, that's what you find. Break the symmetry, and you can deal with it. Here's another network. This one has an axis of rotation right around number 2, like that. You can flip 1 and 3 and you get the same thing. And you can show that for 1 and 3, you can observe out here, but if you look at 2, you can't get any information on it. So that fits, and then we looked at this, and it makes no sense at all. These are pretty simple network motifs. You see these in the mammalian brain. This looks, even in the perfectly symmetric case, using those methods that I just mentioned to you by Letelier and colleagues, you see a completely observable and controllable system. So then you need to go and ask, what's a group representation? And if you look at these networks, there are 3 axes of symmetry where you can flip it over. So those are the little sigmas here. And there are 2 rotational symmetries, clicking once and clicking twice. And then there's always an identity in the group. A representation of a group is a set of matrices that represent flipping and rotating these structures. So that's all a representation is. but there's still a problem. If you look at Lynn, I blame it on the cactus. Lynn's paper is a classic, and it's constantly mentioned. It is utilized in all of those nature papers that we mentioned. Here's the hard paper. Lynn's paper is easy enough so that if you go to med school and you have a little patience, you can sketch out the solutions to simple networks. It's really beautiful. I love that paper. This one is brutal. This is David Rubin's thesis at Columbia in 1971. He gets it published. It has 3 citations. I call this control theory archaeology. It really never got any citations. This is the Max Stead. If you write something that nobody can understand, no one will cite it. But Rubin figured it all out. Now, we didn't actually understand this paper, but we got Columbia to send us his thesis, which was still in bound form. I don't think it had ever been cracked open, but it was in the library, and his thesis explains enough to figure out what he's doing. This is what Lynn needed to read when he goes and publishes his classic paper, because it tells you how to reduce those matrix representations of things like neural networks, and it turns out to be exactly the same problem that these scientists use in the Pecora paper to reduce the connection matrix and ask what pieces of a power grid synchronize with each other, as what we ended up needing to do to explain why this and this are not observable in the symmetry axes, and this is completely and always observable. Cyclic symmetries turn out to be completely understandable if you're dealing with a network. And to make a long story short, it's the class, whether it's rotational or it's reflection symmetry, that determines whether it's observable and controllable. And this really extends the cactus view of networks to include networks with symmetries. We wrote this out in a paper that just got published in Physical Review. Well, so what? Well, this defines what you can learn about a network. And the specific problem that you folks in the audience face is how many electrodes do you need to use to get a given amount of information out of a neural system? That's number one. Number two, how many electrodes do you need to get a given level of control out of the system? This is one of the flaws in our presidential brain initiative in the US. We had hoped that if you just record from enough neurons, you'll understand what the network is doing. And it's not so simple. You need to have some understanding of the symmetries that are present. And of course, I mentioned you're not going to go into electron microscopy on everything that you record from, but you can infer some of the symmetries present from the amount of synchronization you see. It's also an important missing link, I think, with the seizure prediction. It defines what you need and how well you can observe and how well you can predict a network. So, a couple of group facts. Thank you for bearing with me. Most of you stayed awake. That's pretty good. I just want to thank the organizers for putting all this together, especially Levin, who I think is like almost single-handedly gotten all of us together here. Also, this rather marvelous city. I actually had a day or two without working. This has some of the best music and art in the world here, and do try to take a little bit of time to see some of it. And of course, the other group here is my colleagues, Andrew Whalen, Sean Brennan, Tim Sauer. Andrew is the PhD student who literally just spent 5 years trying to work through a lot of this. And we archived the code that he wrote with the journal paper. It is very difficult to get the Lie derivatives and the Lie brackets correct in order to make these measurements. So we're giving it all away in case anyone here is so disposed as to try to work with this. So thank you all for your attention. I'm happy to answer questions. Yes.
So I have a background in physics, so maybe I'll ask a question. So I'm a little confused. The original part you talked about the algebras, and then later on you talked about permutation groups. Well, the algebras are continuous groups, and permutations are not continuous. So what are the groups related towards?
This is all. That's a very good question. I'm going to use the assumption, which I don't think is necessarily true, that the only thing that's important here is the permutation group. You see that in a lot of the description of other kinds of graph-directed networks like algorithms. I'm not sure that's the case. I mean, if I were to ask you, what is it about the symmetries in the Roman network that are important in terms of observability? I could ask, what about inversion symmetry? If you're dealing with molecular vibrations, inversion symmetry, of course, is the center point that you could reflect all of the atoms through to make an inverted molecule. Are we sure that's not important? Asking whether you could observe from a neural network. Those are open questions. But everything that I've shown here is all discrete point groups where one can swap those components, much as they do in chemistry. And so the lead structure and the algebras apply to that. Getting to your question?
I'll talk to you later.
All right. Yeah.
So in the last time, you mentioned that this is relevant for Seizure prediction. And I was wondering what your thoughts are about seizure control. So you kind of, like, once we establish that a system is controllable in the abstract, how do you think that, what are your thoughts on bridging the gap and kind of developing algorithms that can be used in a clinical setting, for example, for simulations, how to actually control the network?
I think this framework applies to those questions. And it specifically applies. There's a nice figure. If you go back to from Barabachi's paper, where they actually kind of illustrated where are the various points you would need to have an electrode present to be able to fully control such a system. Now, that's a loaded statement. You have to fully control a system. Now, there's a number of ways of defining that. I could say that if I took each of these variables, full control means I can push it within its domain of excitability. I can push it to any place in a finite period of time. If I want to prevent an oscillation or get you out of an oscillation, if this is it, I don't need full controllability. I do need controllability for the particular dynamics you want to either stay in or get out. So we face a simpler problem in terms of seizures, but this is the framework that in the worst case scenario, this is a way to lay out, at least here with linear theory, where you would need to put all of your control points based on the cactus formulation. So I think this is extremely pertinent issue applies to devices that like many. What else can I try to answer?
Thanks, Steve. Any type of model that we deal with that's going to be this sort of elliptic scale, that's going to have some sort of uncertainty involved, how does this theory deal with that? Most models are going to be incomplete or be somewhat inaccurate, and it seems like this sort of theory requires you to have exact knowledge.
Actually, it doesn't. Well, one of the beauties of Lynn's genius was to realize that what mattered weren't the values, it's the zeros in the network structure. And what he showed is that if you in fact have a network of a given topology, almost any value that connect the nodes to each other would remain controllable, or in the inverse, observable. So actually, it's an extremely powerful view that speaks directly to what we face in neural systems, which is that because of the inherent variability, sources of true stochastic dynamics, and our bad measurements, we never know the values of any of this precisely. And in terms of the whole framework I'm discussing today, we don't need to. With the exception of the purely symmetric cases, which, of course, you'll never see. All of this is the nonlinear world of looking at observability and controllability is quite different from the original linear theory, which is a yes or no question. Could you completely reconstruct the reasons greater than none? And all the metrics I'm showing you today that I briefly touched on are measures that start from very small bits of observability to large degrees, but it allows you to go and provide, I think, what's much more relevant to us, which isn't perfect. What degree of partial information do you learn? How do you partially control those? So I think we're okay. Yeah.
What would happen if you have an evolving network where nodes come and die and links come and die? What do you do in this case?
Oh, they asked me something like that. I don't have a good answer to that, but I keep thinking while I'm trying to get out of your question. I keep thinking of one of Lynn's proofs is that you're structurally controllable if by removing edges you can get down to a calculus. And so evolving beyond the fundamental topology that answers the question whether you can observe or control by adding additional edges, you still stand by the relevant topology. So in some ways, I could see that some evolutions still preserve the nature of the network in terms of its metric. But of course, if I put out the wrong effects, I can isolate a few pieces of the network. That may go on as amateur, I can think of all kinds of ways that I can control it. And I can't on my feet come up with any very sense. Any other questions I can try to answer? Yes.
So where does identifiability fit into this? So if we're just working with functional observations, say, can we determine where the ones and the zeros are, even if we don't need to know the weights?
I hope so, but I don't have much of a better set of thoughts to answer that hard question than I do for Klaus's hard question. But I do think if we can try to identify for measurements relevant pieces of topology, and I think what saves us is the Epilepsy. Actually, it's a theorem by Stewart and Stewart and Parker, which is based in conjecture about previous. And I think in essence that really does provide us the experimental hook we need to ask if by observing synchronies in your networks you can back out some of the topological information. You can also turn that question around and ask, well, if I don't really know the topology, can I try certain classes of topologies in order to, as you say, identify zeros? I hope that's true, because
All right. So next.